All right, let's run through the flowchart one last time. Your first stop is to see if you have a recognizable form. So a geometric series would be a constant raised to the n, or a p series looks like n raised to a constant. If you don't have either one of those, then you want to try the divergence test, which means you're going to take the limit as n goes to infinity. If that is not equal to 0, then your series diverges and you're done. If the limit is 0, then you need to look and see if you have positive terms or alternating terms. So for positive terms, we have the integral test, which is great if you see a recognizable antiderivative or a u-sub. The direct comparison test is good if you have a constant over a polynomial. Or if that fails, the limit comparison test is your next go-to. Or if your series looks like a polynomial over a polynomial, limit comparison test is a good choice. For alternating terms in your series, we have the alternating series test, which if you have a clear blinker, this is a good choice. If you have something that looks like factorials or n to the n, you'd want to use the ratio test. And then the new test that we're going to learn, this is our last test, is if everything in your series is raised to the nth power or the 2nth or the 3nth, something like that, then the root test would be the one to use. All right, so let's take a look at the details for the root test. Here we go, let's zoom in. So for the root test, what you're going to do is you're going to take the absolute value of your series, and then you're going to take the nth root, okay, which should get rid of it being raised to the nth power, and you'll take the limit as n goes to infinity. And here's our criteria. It turns out this criteria is exactly the same as the ratio test. If you've memorized it for the ratio test, you also know it for the root test. So that means that if the limit L is less than 1, then we get absolute convergence. If the limit L is greater than 1, our series diverges. And if L is equal to 1, then our test is inconclusive. You need to do something else to figure out if your series converges or diverges. All right, so let's give this a try. We have the series n equals 2 to infinity of 4n minus 5 over 2n plus 1, that whole thing raised to the nth power. So let me slide this up here. This is number 18. So L is going to be the limit as n goes to infinity. So I have the nth root. I'm going to take this absolute value here, 4n minus 5 over 2n plus 1 to the nth. We'll close out that absolute value there. So I have the nth root of something to the nth power. So this will give me the limit as n goes to infinity of the absolute value of 4n minus 5 over 2n plus 1. And as n goes to infinity, I have a polynomial over a polynomial, so I'll take my leading terms in the numerator and denominator. This is equal to 4 over 2, which means that this limit is equal to 2. And I'm ready to write my conclusion. So since L is equal to 2, which is greater than 1, my series n equals 2 to infinity of 4n minus 5 over 2n plus 1, all raised to the nth, diverges by ROT for the root test. So there is our conclusion statement.